Okay, so what are we in designing the agents? On Tuesday, we talk about a little bit about agent, right? And we said that agents are doing something for us, and especially solving a problem or doing some task for us. And let's say, okay, here, if you are a designer of a system and have to implement the system to solve a problem or doing some task, what do you have to do? What do we have to do? Yeah. First, I think like we have to know about solution, right? Because we are expecting some solution. Determining what constitutes a solution is very important. And since it's not you to solve the problem directly, you have to represent the task in the way a computer can reason about, right? So it's not you, but the agent who solve the problems. And answers or actions or services should be provided as an output of agents. And here, the agents are a computational entity. Then the output should be interpreted as a solution to the task, right? And here are the things you have to, here's the thing, slightly different according to the type of the system you will design. Maybe you can design a system working based on some heuristics and algorithm, or maybe just using some predefined procedures. In that case, maybe you have to specify how to compute something and how to specify what the next step or this and next step is. A designer or as a programmer, you need to figure out how to do the computation for the task, right? If we rely on some algorithm or heuristics. But what if you design an AI-based system? In this case, you have to specify what needs to be computed instead of how to do it. So you're not teaching how to do it, to the agents, but more likely you have to teach the agents what needs to be computed. And you need to tell how the world works, logics, rules, and something like that. And anything about the world, you have to teach them. An agent have to figure out how to do the computation. So it's not you, but agent to figure out how to do the computation as a process of solving the problem. And many agents interact with people, a human. Often a goal or a task is given informally because we are not formal, right? So when you talk to your friends, you talk in informal way. So maybe the goal or task is given because from you is informally in terms of human language, such as maybe for the case of delivery robots, maybe you can just order that or deliver parcels promptly when they arrive or something like that. And here, one very important thing we have to consider is a representation. So representing something that has to be computed is a very important thing when you're designing agents. Okay. The representation is kind of format or formal description about the task. And any information about the task has to be encoded in this representation. How the environment works, what the goal is, and what kind of inputs are given or something like that. Once a task is represented, then the agent. So here, hold on. So once task is represented, and here we're gonna have a representation about the task, right? And the agent is time for the agents. So agent, the computation agent can compute the task represented as this the representation. So So agent is now to compute the representation. And from that point, actually agent doesn't need to care about the task in the human level, right? So it is already represented as a representation. So agent doesn't have to care about this task, but more care about this representation. So it is just enough, but to care about this representation. And after some computations on this representation, output is obtained, right? And we can interpret this output and say we get the solution. So informally, or maybe in human language, we can define task and roughly the solution, right? So this is the informal space. But for the agents, it's not like this. So we need a formal description, formal space where our agent solve the problem. So here is the space for the agent. And the 3 steps, yeah, 3 steps, represent, compute, and interpret are very important. The core processes in designing agents, and especially the representation and the computation is the most important thing that determines the quality of the agent. So in general, as I mentioned before, when you use AI in your agent, it's not how. It's not how. It's not how. But what task or solution has to be represented is the important things. For us human, it is easy to define a task and solution in human language, but in the definition or description of the task, much is typically unspecified. It is because we used to talk based on our knowledge or background of common senses, so we skip a lot of information. So the lot information is unspecified. This is why it is hard for computation agent to correctly understand the task. Otherwise, the agent can start solving the problem properly. I think we all have some experience about this. When you use AI speakers or chatbots and something like that, they're not like us. So many times they don't understand you, right? And so you have they ask you to say again and again until it understands you, right? It is because the difference, because of difference between human description and agent description. So it's quite difficult things. But much work of AI, this is why motivated by common sense reasoning, including language understanding, to deal with this unspecified information. So this is one reason why it is so difficult. It's still difficult to represent the task and solution in agent language. And what about the quality of solutions? So in many cases, the types of solutions are different from each application. So the solution is not all the same. So there are some categories, the classes of solutions. It's not like kind of math problem where you have a correct answer or not. There are several categories, the class of solutions. The first one is optimal solutions. And so we have to measure the quality, and we have to say that this is optimal, or exactly what we want or something like it. And the another one is we have satisfying problem as a solution. Whatever, as long as it satisfies some condition, is okay. So it is good enough according to some description is adequate. And there is another category, the approximately optimal solution. Sometimes we call suboptimal solutions, something like that. And In many cases, we don't need an optimal solution all the time, right? Sometimes just suboptimal is good enough for us. So we don't want to spend too much time and too much effort to find this optimal solution. Rather than that, we just satisfy with suboptimal, approximately optimal solutions. And the last one is another one. Last one is the probable solution, which is the one that is likely to be a solution. So we may not know if could be a real solution or not at that moment, but no, we can lawfully say that, just say it's probable. So it's kind of candidate solution. It could be a solution or not, but at the moment we can say that it could be a optimal solution or suboptimal solution, something like that. So this kind of category is very important. It is because in practice, we are not all the time considering the optimal solution. So we can just have to satisfy with suboptimal or probable solution at some point. Okay. And decision and outcomes. Decision and outcomes are not going along with each other all the time. So sometimes good decision can have bad outcomes. And also the bad decisions can have good outcomes. Because it's not all the time true, it's sometimes, right? In general, like good decision with the good outcomes and bad decision results of bad outcomes, right? And to make a better decision, we need more information about the situation, task, and environment. And here we say there is the value of information. So this is very important in practical situations. And we're gonna cover this later when we talk about the probability and Bayesian network or something like that. And also in the real world problem, we have a trade-off between time and quality. So here's the time and the solution quality in general. So if you have enough time to compute, you can get a better solution, right? Because you can spend more time to compute the solution. But if you don't have enough time, you have to find you have to, as I mentioned before, you have to be satisfied with a suboptimal or maybe just probable solution at least, because you don't have enough time. And in practical situation, people like to use anytime algorithm, which is an algorithm that can provide a solution at any time. This characteristic, this feature is very important in practice. So an algorithm that can provide solution at any time is very important. It produces a so far best solution. Not like you have to wait for an hour a day to get answer. It's not like that. You can just promptly answers to your questions. So many people here, right, are the student, I think, like many of you studied deep learning or machine learning or something like that, right? So when you train the model, like it will take a day or maybe a week or a month or something like it. It's not like that, right? It has to give you an answer whenever you want. This is any time algorithm. And especially the responsive or interactive agents use such kind of the anytime algorithm. And some agents are not just searching a right or good answer. They may try to get more information to get a better solution. So through the interaction with the environment or the people, they try to gain more information to make a better decision. In that case, it's more likely to have more chance to get the better solution. It is true because you gain more information to get to the solution. And we'll deal with this issue more later with Bayesian and decision networks when you study that. Okay. Oh, yeah. And in many applications, and this is very important, the graph, the quality and computation time. So in many applications, the quality of solution is degraded by time. It is true, right? So if you ask some solution, and if it is giving you the solution right after that, it will be the best. But maybe after a day, you don't need that anymore, or something. The quality or necessity of the solution is not that much high, right? So we love to assume that there is time discount affecting the quality subjective to the user, and solution has here. So here there could be some sort of like kind of absolute value. So solution could have absolute values, but because of this time discount, you have to subtract this time discount, and then you will get this discounted quality. So the value of solution will be like this, discount of quality. So this is why like the anytime algorithm are quite useful and important in many cases, because you can trace this kind of the discounted quality, and you can just make a decision here. Oh, I'm gonna use this solution. I'm gonna use this solution, something like that. But if you don't have this kind of anytime algorithm, you don't know until you finish, until you find this absolute, the optimal value, optimal solution, but it's already too late. It's not like kind of optimal for you in the time sake. Yeah. If you have any questions, just stop me. Okay. Ask. Keep watching the chatting window. So if you have any questions, let me know that. And let's get back to the representation again and talk about it a little bit more. Okay. So what do we have to do? What do we have to represent? In designing agents, we have to represent the world in general. So we have to represent the environmental world, and what the different configurations can the world be in, and how do we denote them is the core thing in our representation process. And this representation implies some states and possible worlds and something like it. So we may say that the configuration could be a state and also the possible worlds. Yeah, let's think about the chess game. So in chess game, what we have to represent is the board status itself, right? And in addition to the this representation and the word, it also has to represent how the word works, right? This is also very important. So not just represent the situation, but at the same time we have to represent how the word works. It's kind of rule of playing the chess game or something like that. So here we have a constraint and also causal, or yeah, and what is this? The action, precondition, and effects, and something like this. So the maybe constraints is something like kind of sum up the current into a node should be 0 or something. It's kind of rule. And causal is like kind of what are the causes and effects of the brain disorder, something like that. and actions, precondition, and effect. Whenever agents have specific actions, you have to satisfy the preconditions. And after performing the actions, it will have some effect. So what can I press, or when can I press this button, or what happened if I press this, something like that. Those kind of information should be encoded into the representation as much as possible. So all the things have to be represented so as the agents can compute based on these informations. So perform the doing the task. And what representation we can say good? So not any representation, maybe not all the representation have the same value, right? So some kind of representation we can say is good. Some other representation is very bad. So how can we say that? The representation itself has to be rich enough to express the test, right? Or about the task. Otherwise, we can represent or we can describe, explain the task correctly. So it should be rich enough. And at the same time, it would be good if it is very close to the problem as possible. So it has to be compact and natural and maintainable. Then we can say this is a good representation. It is because it is rich enough to express the idea, the knowledge, and it is close to the problem as possible, and compact, natural, maintainable. So we can say that is a good representation. And the resources, the computing or memory, whatever this kind of stuff is limited in practice. So the representation should be amenable to efficient computations. Always there is a trade-off, right? Since it's the same working in the real world. Maybe we can say that I think all of you know about the Go, right? So the Go match, in a Go match, there's a time limit, right? So one player play and take turn, the other play, but both of them maybe some given 1 minute, 2 minutes of thinking. So there is a time limit. And what about the quiz? So show like kind of Jeopardy also has some time limit, right? So that's why like kind of IBM Watson is specially like designed to answer for a given a few minutes. I heard that like kind of maybe just 30 seconds, it has to arrive to the answer. It's kind of any time algorithm, right? So for given 30 seconds, it reaches to the suboptimal or quite optimal like kind of answer and give. Yeah. And how about the knowledge, like knowledge part? The representation should be interpretable and well constructed. So it has to be constructed either from people or from data. So for experts, if he's designing the agent, this kind of representation, it should be easy to design, right? Otherwise, it's very difficult. That's why like kind of the knowledge system, expert system in AI history, they try to kind of get the knowledge from doctors or some sort of like kind of experts to design such knowledge into a rules and some sort of like kind of representations. But the difficulty is how to kind of translate or how to map to the real knowledge to the representation is very difficult things. So if the representation is difficult itself or maybe complex itself, is very difficult to deliver the idea, right? So it should be easy for expert or designer to use the representations. Or like maybe you can use machine learning. So the data or the past experience, they can update the content of the representation. So in this case, getting a volume the data set and using them should be also very easy Otherwise, not that much practical to update the agents. So how to design such kind of the representation is the key of designing a good intelligence agent. Since the agent work on a computer, right? The base of the agent is computer, right? Maybe computing kind of the units or device or something like that. So the level of implementation covers very broadly. It's up to the platform you're gonna use. Maybe you can use some like kind of the hardware or maybe some embedded module or kind of supercomputer or whatever. In that case, like kind of you can apply the complex or maybe sophisticated the language, and such as like kind of machine learning language tool or something. And sometimes the C++, Java is practically applicable, but some embedded system like kind of you can at most you can use C, or like kind of you can use kind of the low level programming, something like that. Or maybe some system you can use English itself. So like kind of the chatbot or AI speaker. There are several attempts to use just natural language to make the coding or something like that. So it's very up to what platform you're gonna use. And for a given platform or resources, the representations are designed hierarchically. If you're involved with the hardware, you may have to design digital circuits or embedded system coding or something like that. I think we are kind of software engineers, AI researchers. So I don't think you have to deal with those stuff, but you can just deal with the high level specifications or the program language at most. And I believe some other one will do lower stuff for us. But anyway, if you know this kind of the platform, you have to find a proper representation for them. And since the intelligent agents probably cover pretty much of these parts, so it'll be good for you to understand this kind of architecture, the hierarchy of representation. And as I mentioned earlier, the representation is to present the world, right? The goal of and the function of representation is just to represent the world. And here the world includes the environment and also the agent itself. And we have one common the concept called physical symbol system hypothesis, where we can express all the things in symbols and also symbol system theoretically. It's not like kind of practical, the model or hypothesis, it's just for the theoretical. So more things are started from the theory, and all simulation, you can just do this and that before it is deployed in the practice. And this hypothesis provide some fundamental basis design from the simple to complex agents. And the representation has to express and to include two levels of abstraction, and knowledge level and symbol level. And knowledge level here is about what an agent knows and what its goals are. And symbol level is just kind of the simple description that agent reasons. So knowledge is to represent external the world to the agent, while the symbol level is just for the implementation of the such knowledge in agents. So we have knowledge, and also we have symbol, and symbol gonna be implemented. It's gonna be used to implement the knowledge. So in agents, we have a lot of symbols that kind of organize complexly combine together to implement this knowledge. So practically, there are several things we have to consider. And here are some of them, some questions. So the most difficult and important thing is how to map the problem to a representation. So here, there are many questions, but here we highlight the 4 questions. What level of abstraction of the problem to represent? And what individual relation in the world to represent? Something like that. How can an agent represent the knowledge to ensure that the representation is natural, modular, and maintainable? It is very practically important. And how can an agent acquire the information from data, sensing, experience, or other agents, or maybe from people or something like that. So this kind of stuff is very important in designing the representations. Okay, and in representing the word, we can choose the level of abstraction. So there is a higher level and lower level. And higher level description is easier for a human to specify and understand. This is like kind of the human language, the natural language is very high level, right? And lower level can be more accurate and more predictive compared to the high level descriptions. It is because like kind of coding. So whenever you code, there is no ambiguity, right? It's all the time clear because there is a basic logic and rules. And according to those rules, the sentence is clearly interpreted. But what about high-level descriptions? High-level descriptions is like you omit a lot of stuff, right? It is because it is very high level. So it's very surable for human, but it's not like kind of for the agents to understand that. So they high level the description abstracts away details. So they don't care about the details. But this detail may be important sometimes, actually in solving the problem. But high level description, they don't care about it. Sometimes it rely on some common sense knowledge or something like that. And there are, we have some pros and cons for each of them. It's up to the problem and user developer platforms. And many times you have to use, I think, like multiple levels of abstractions. So it's not like just one thing. I'm gonna use high level description only. It's not like that. I'm gonna use the low level description only. It's not like that. As I just show before, like the problem is like this, have this kind of hierarchy. So sometimes you can describe the solution in very high level description, but some other time you have to go lower and lower. So this is the, so far we just like kind of ramble this and that about the issue of designing agents. And let's have a very short break, a 5-minute break. And then we continue to cover all the design space of intelligence in more detail and more systematically. Okay, let's have a break until 11:20. And we're gonna cover just 10 to 20 minutes. Have any questions? Have any questions? No? I'm not sure you can hear. Oh, okay. Oh, one thing I have to mention that. Please turn on the camera. Oh yeah, I forgot to tell this. So yeah. Anyway, I have to check the attendance, right? So in the middle of the class, I'm gonna ask you to turn on the camera And that time I'm gonna check the attendance. Will be okay, make sense? Right? So in general, you don't have to turn it on. You can just turn off the camera, but at some point, I'm gonna ask you to turn on the camera. And then that time I'm gonna check. So if you're not there at that time, we'll see. I'm not consider that as absent, but yeah, it won't happen. Yeah, but oh, okay. Yeah, in that case, if you don't have a camera, but if you have your friends next to you, yeah, you can just stand behind of him. That will be okay. But anyway, you have to show your face that moment. And I'm gonna, yeah, I don't know. Oh, yeah. Oh, yeah. Okay. Yeah. So yeah, we'll meet at 11:20. So yeah. Okay, today is just a practice. We're gonna yeah today just practice, so it's okay to turn it off again. Oh, symbolic level. What? Oh, okay, there are some questions on the chatting windows. Actually, I already uploaded the presentation material, lecture material. So you have to download the chapter 1 again. And then symbolic level. What do you mean symbolic level? So symbolic level, symbol level, knowledge level. So anyway, you know what, like kind of knowledge is like more abstracted and higher level concept. Maybe, for example, playing chess and playing these, understanding some like kind of rules and strategy gonna be a knowledge. And symbol is like kind of the basic entity. Maybe the player, what is that? How can I say that? 말을 뭐라고 하죠? 말을 영어로 뭐라고 하지? 빨리 찾아봐야 되겠네. 말이 말하는 말이 아니고 게임 말인데 게임 말을 뭐라고 하죠? 우리 태화 씨, 태화 씨 어디 갔어? 우리 태화
네.
씨가 일할 때 딱 항상 얘기해 주는데.
저도 잘 모르겠습니다.
아니 태화 씨도 잘 몰라요? 기물.
네.
그러니까 뭐 체스 같은 거 할 때 플레이하는 그 말이 있잖아요. 그 뭐라고 하지? piece? Oh yeah. Chess piece. Oh yeah, marker piece. Oh yeah, that would be good. Anyway, when you play a chess game, right? There is a piece of marker or maybe piece of characters or something like that. That's gonna be a symbol. And also the chess board, the each location, the place gonna be another symbol or something like that. So symbol is like kind of very basic element entity to describe the knowledge. So the important thing is like kind of, we all know about the knowledge. The difficult thing is how to implement that into a symbol level. That is very challenging issue. And nowadays, old-fashioned AI is like kind of doing all the thing in planning. So they try to map a symbol, try to map the knowledge into a symbol level. But nowadays, the deep learning world, right? So we don't care about that. We just input the data and the machine neural network, whatever, you're gonna do it for us. So we don't want to care about that anymore, something like that. There's a kind of new fashion, the deep learning style approach. Okay, I couldn't have a break, but already started. Get to the 11:20. Okay, another question. Compute have a solution. Agent computer. Oh, okay. So the thing is like this. Hold on. Here, right? Okay. So, how can I say that? You are almost die because you are hungry. So you need the food at that moment a lot. Okay. So, but once time goes on, and no, this is not a good example. We'll say. 이건 한국말로 할게요. 이건 한국말로 할게요. 지금 왜 화면이 안 바뀌지? 잠깐만. 잠깐만요. 이게 참, 난 바꾸고 있었는데 제대로 안 바뀌었네. 요거였죠? 잠깐만요. 자, 요건 한국말로 할게요. Forgive me. I have to speak in Korean. Yeah. 이게 무슨 얘기냐면, 내가 필요로 하는 그 솔루션이라고 하는 것이, 그러니까 이게 이제 예를 들면은, 언제까지 이게 필요해 라고 딱 시점을 정해놓으면 그 시간 안에만 구해지면 되죠. 그 시간에만 구해지면은 사실 타임 디스카운트라는 건 사실 없는 거예요. 근데 이제 이게 그냥 지속적으로 계속 생활하는 로봇, 아니면 생활하는 그런 에이전트다. 지속성이 있는 에이전트라고 하면은 내가 이 서비스를 언제 시점까지 받을 필요는 없는 거예요. 그러니까 예를 들면은 어떤 거 다시 그 뒤에 또 다른 예가 나오긴 하는데 트레이딩 에이전트다 라고 하면은 이 트레이딩 에이전트가 어떤 솔루션을 딱 찾았어. 근데 그 솔루션이 옵티멀하지 않은 솔루션이긴 하지만 예를 들면 잠깐만요. 예를 들면 요 시점 봅시다. 시간이 계속 지나가면서 내가 그 솔루션 말고 다른 솔루션이 계속 생길 수도 있고 얼터너티브한 일들이 발생할 수도 있고 내가 이제 그 꼴이 항상 유지가 되는 건 아니죠. 바뀐다는 거죠. 계속 바뀌긴 하기 때문에 지금은 당장 배가 고팠어. 그래서 누가 나한테 뭘 주면은 내가 너무 고마운데 조금 지나서 그만큼 배가 고프지 않게 됐어. 그러면은 누가 나한테 뭘 줘도 그만큼 고맙지 않은 거죠. 그런 맥락이에요. 그러니까 그냥 아주 단순하게 프리미티브한 어떤 솔루션에 관련된 얘기라면은 좀 다른데 이게 이제 복합적으로 내 꼴이 그만큼 계속 유지가 돼. 이게 어쩌면 다를 수도 있어요. 점점 배가 더 고파져가지고 그거에 대한 가치가 더 높아질 수도 있긴 하지만 보통의 경우에는 그 꼴이 이제 그때만큼 필요로 하지 않게 된다라는 게 일반적인 상황. 그런 경우 대부분 이렇게 이제 표현을 해요. 여러분들 검색 같은 거 하죠. 지식인의 답을 질문해 본 사람. 여러분들은 그런 세대가 아니죠. 지식인의 질문 올려본 적 없죠. 호택 씨 웃기만 하지 말고요. 그 지식인에 올려봤어요? 제가 네이버 있을 때 저희 팀이 이제 지식이나 이런 거 관리하는 팀이었는데 저는 네이버 오래 있지는 않았지만 이게 문제가 뭐였냐면 지식인이 처음에 나왔을 때는 답변이 엄청나게 많다가 요즘에는 이제 거의 질문도 잘 안 하고요. 답변도 별로 없어요. 다 이미 있어요. 그래가지고 업데이트가 안 되는 거를 되게 걱정을 많이 하고 막 그런 얘기들이 있었는데 이제 지식인에 글을 올렸어. 올릴 때는 되게 다급하지. 근데 하루가 지났어. 답이 안 달려. 이틀이 지났어. 답이 안 달려. 더 다급해질 수도 있지만 점점 흥미가 떨어질 수도 있는 그런 상황이 올 수도 있겠죠. 그러니까 그만큼 이제 퀄리티가 바뀐다는 얘기예요. 하지만 그 솔루션의 퀄리티라고 하는 거는 이제 시간이 많으면 많을수록 더 좋은 퀄리티 있는 더 좋은 솔루션을 찾게 되겠죠. 컴퓨테이션으로 뭔가 한다면. 근데 그만큼 시간이 안 주어졌을 때 이런 이제 현상들이 발생한다라고 말씀을 드리는 거예요. 자, 잠깐 쉬고 넘어가려고 했는데 그냥 네, 아주 짧게만 오늘 하고 다음 시간에 이어서 하죠. 호택씨 아니오는 뭐예요? 아, 안 써봤다고? 이게 참, 네, 화상으로 뭔가 하는 거 되게 어렵네요. 자, okay, let's continue, but maybe we can just finish in 5 to 10 minutes. And we'll continue this topic next week. Okay, we'll see. Hold on. 잠깐만요. 제가 뭐 이것저것 좀 켜야 돼서. Okay, so from now on, we're gonna talk about the design space of intelligent agents. And here, so actually, you know what, like the agents are very complex entity and compared to a common object. Although the human is the most complex.